Hi, here is lesson 10a. This is Fibonacci's rabbits. So this lesson is really going to be about exponential growth and how it's more than just saying a population is growing rapidly. So it's a very particular kind of growth. So we're going to continue on what you did in the preview lesson. So they were having you look at the number of rabbits and how they increase. And this was the table that we looked at there in the preview. So the important part of this table really is to look at the months, right, that have gone by. And what we're doing is we're looking at the total number of rabbit pairs and then also the total number of rabbits. And something that was mentioned in the preview assignment is this sequence of numbers is very special. This is called the Fibonacci sequence. And the way that you can get any number in the sequence, right, like the number 5, is by taking the two that precede it, before it, and you add them up. So you can see 2 plus 3 equals 5. And then to get this last column, we're just talking about the total number of rabbits. These are pairs, so all we have to do is to double them to get that number. So the first question here is saying how many rabbits would we have in the 13th month? So in a different screencast, I'm going to show you how to do this in Excel. So this is what the table looks like. It's the same thing that we just saw, except it's dragged down a little bit farther. So if you want to answer the question for 13 months, right, you have to look at month 13. And again, you can see the pattern. 233 is equal to the sum of these, the two previous ones. So to answer the question, how many rabbits, right, that would be this number here. So 466. And an important thing there is the assumption, right? None of the rabbits have died, so that's what we get for that entry. Okay, so let's look at question 2. This one here you can do mostly in Excel, right? So they're saying, how about at the end of 2 years, right? So how many rabbits do we think we'll have? They do tell you maybe make an initial guess, right, to actually think about it, because this will give you a sense of the rapid growth that we see in this rabbit population, and then also use the spreadsheet to determine what you get. So I will, again, just show this here because I'm going to do this in a different screencast. So if you want to see at the end of 2 years, I actually dragged this to month 25, and there is a reason for that. So if you look at the very top, if we take this to be the initial state, and then you look over here at number 2, then what we're really saying is that right here at month 2, this is actually the end of the first month. So if you want 2 years or 24 months, you really want to take that all the way to 25, and then you can get the right answer. So if we want to figure out how many rabbits are there, and of course this is assuming no deaths, we have this number here. It's stunning, right? It's in the thousands, so 150,050 rabbits. So that takes care of that first page. So let's look at page 2. This is where most of the mathematics is going to happen. So this is talking about the average rate of change of the population. And so symbolically, we can write this as what's the change in the population over the change in time. Right? This is just the symbolic way to see this. And so we have a couple of questions here that we can answer. So this problem is saying let's choose some different periods of growth and determine the rate of change, right? So we're going to actually go back and look at this ratio. And we're going to say for the rabbits, are these rates the same? So I'm going to pick some different numbers here from that previous spreadsheet, and we'll run through and just calculate them. So I'll put these over here. I'll just pick a couple of different ones. So maybe I'll highlight this in color. So why don't we do something like, I'll look at 10 and 4, and then we have to look at the time, right? So we have to be consistent there. So what we're going to do here, if you want to look at one of these rates of change, 10 minus 4, right? That's the change in the population. And then the change in time, 5 minus 3. So here we're going to get 6 over 2, or 3. And when we try to interpret this, this is 3 rabbits. And the timestamp is months, right? So this is per month. So that's just one calculation that you could do. So this is saying, well, what happens if you pick different data values, right, in which to do a similar calculation? So I'll do that as well on one more. So for example, how about I grab 288 and then maybe this 2, right? So let's see what that looks like. So this is the change in the population. And then the change in time, this would be 12, and then we'd also have 2. So that's what that looks like there. And so here, then we have to go through and do the mathematics here. So you get this here. The point here, right, 288 minus 2 is 286. You get something here that's pretty close to 28. And so we would interpret this the same way as this number here. And so we're getting 28 rabbits per month here as an increase, and then here we're getting 3 rabbits per month. So it's saying, are the rates the same? They're definitely not. And what this is telling us is that the growth of the rabbit population is not linear, right? Because if this were a straight line growth, then these numbers would actually be exactly the same, and they would be the slope of the line. So because these are different, that's telling us we don't have linear growth. All right, so let's run to number 5. It says, can you find any relationship between the rate of growth of the population and the size of the population? So we're going to do a couple of different miscellaneous calculations here. All right, and so I'm probably going to, for simplicity, just use the rabbit pairs because the pattern here is going to be pretty much the same. So I'm going to go back to this table here, and we'll do a couple of these calculations. So they're telling us in the problem, maybe look at months 9 to 10. So I think they start off by having us look right in this section here. So I'm going to do that to start. I'm going to look at that there. And in this problem, they're not saying to compute the average rate of change, but this is the relative change. All right, so we're looking at the rate of growth to the size of the population. So we're doing a slightly different calculation here. So if we look at 55 minus 34, right, so these are the rabbits, and then divide by the old population, which is 34. So we can just run through and calculate that. So we get this number here. If you check this on a calculator, you get something around 0.6 or so. Now what happens if you try that on a different adjacent set of values? So I'll do something different here. Let's try, for example, maybe this one right here, right? The 233 and the 144, because this is kind of curious what happens. So same pattern. This here is new minus the old, and then we're going to divide by the old. So we're just doing that calculation. So if you check this out on a calculator, you might be a little bit surprised, but you pretty much get the same number here. All right, so that's an interesting little thing that's happening there. So this constant here is very, very close to 0.62. And we'll be looking at what that means, right, in answering some of the other questions in this lesson. So let me make sure here. So that looks like we've answered question 5. Okay, so on to question 6. This is saying if the current population is size 100, can we use what we have found, right, to actually find a formula for the population size the following month? right? So I'm going to bring back this one here because this gives us all the hints we need to actually do this calculation. So we're going to do this kind of thing. So they're really saying, suppose we know that the population were a certain value like 100. Could we use that to then figure out this one here, right? And that would be like 55 is unknown. So the main piece of information we're going to use here is that you get the same constant, right? Or something very, very close to 0.62, right? Every time you do this. So you can do this for size 100. You can do it for size 1000. It should look very, very similar for both. So I'm going to set something up that's going to follow this pattern that we see. So I'll grab this piece of paper. So let's say the new entry is something we don't know. So this is what's unknown, and this is what we know. So this is like new minus old divided by the old, and we know it's going to equal that constant, right? That 0.62. So then you can run through the mathematics here to figure this out. So if we multiply both sides by 100, we get this here. And this one you can solve actually by guessing, because if you put 162 here, that will solve this equation. So that's 162. So you can pretty much follow the same pattern, right, for the 1000, right? So I'm going to go through and we'll do that as well. So this is going to be new minus old over the old. And this is equal to this constant. And then just go through the mathematics to solve this. So if we take this times 1000, this will give us 620. And then we can, again, figure out x. Right, so x will be 1,620. So the thing to make sense of here, right, to answer this question, we're saying that 100 was the old, and now we've jumped to 162. In the second scenario, 1,000 was the old, and now we've jumped to 1,620. Right, so that's the pattern that we're seeing. So they're asking us in this question, let's see, what multiplier should you use to determine the population in the following month? So we want to say, what number do we have to multiply this by to get this number? And the same question we're seeing right here. So the multiplier that we can see, or we can say it's like a scale, is 1.62. So if you take the previous number and you multiply by 1.62, you're going to get this entry here. So that's something we can use in the next question. All right, question number 7. Can we use this constant, right, to estimate the number of rabbits at the end of 3 years? So if you recall, we already have the number for the end of 2 years. So I'm going to recall that here. So that was this entry that we had seen in the spreadsheet. And so what we learned from problem 6 is that we can take this number and multiply it by 1.62, and you can get the next month, right? So you can get that next quantity. So if you want to go from 2 years all the way to 3 years, that means we have to multiply by the 1.62 12 times, right? And then we're able to get the number that we want. So let's see if we can do that. All right, so I'll grab this piece of paper here. So I'm going to write down that number at the end of 2 years. Right, so that's this number here. And so if we multiply this by 1.62, we'll have 2 years and 1 month. So what we really want to multiply by is 1.62 12 times, right? So you could say to the 12th power, and this would give us the number that we're looking for. So I'll let you check this on a calculator. I would recommend this part first, 1.62 to the 12th, and once you get this quantity, then multiply it by that 150,050, and what you end up getting is something really close to 50 million. Right, so 50 million rabbits. So we could just write it this way if you wanted to, 50M. And that answers question 7. All right, so just one more here. Question number 8. So this is saying, this is about population control, right? So suppose we want to cap the rabbit population at 2,000, and it says it's going to take us 2 months to actually do that. And then it asks, at what population size should you begin to implement your population control? So let's see if we can answer that. I'm going to bring the table back. So the key number here is 2,000 total rabbits. So if we look at our table, we should be looking in the last column, right? Something close to 2,000. So we're definitely drawn to this number, right? That 1974. So this is pretty close to your 2,000. And if it's going to take you 2 months to implement those procedures, then you have to go back 2 entries right here, right? That's 754. And then we would look across right here to that 14. So this would tell us 1 year and 2 months in, right? That's when we would actually have to implement the procedure. Because if we do nothing at all, right, then after 2 months, we'll be at the 2,000 rabbits. All right, that's it for 10A.